All right. And thank you for giving me the opportunity of presenting this joint project with Qinqi Chen and Carl Frey titled Disrupting Science. Let's begin with our motivation that is based on a few facts. First of all, the share of distributed teams in scientific research, and by distributed team, I mean a team composed by members that are not physically located in the same institution, has increased over the last decades. And this increase has accelerated further after the 90s with the so-called ICT revolution. At the same time, we have a large literature from different fields emphasizing that face-to-face interactions are crucial in science and innovation in order to stimulate creativity, serendipitous discovery, as well as the transmission of tacit knowledge that is not easily codified. In this paper, we will show you that a parallel trend is a decrease in the share of disruptive scientific discoveries, a trend that is started around the 70s, according to our data, and is continuing nowadays. Now, to be a bit more precise, I will show you this chart that shows over years the share of teams producing disruptive research, the solid line, and the dashed line that is share of distributed teams. I will be more precise about what do we mean by disruptive research in a moment. So the basic question we ask in this paper is the lack of face-to-face interaction that is responsible for the decline in disruptiveness. Now, let's discuss how do we measure disruption. Our central problem is that the number of citation counts that is a very familiar indicators of research productivity is not going to tell us much about how novel, how disruptive an idea is. Just an example to clarify this concept. Consider two very popular papers in physics. One about self-organized criticality from Bach, Tang, and Wiesenfeld, the BTW model, as it is often called, and a paper by Davis and Kotos from '95 about Bose-Einstein condensation in gas of sodium atoms. Now, these two papers are very popular. They have a similar number of citations, I think in the around between 6,000 and 8,000, the both of them. But they differ in one crucial dimension. The BTW paper is typically cited without mention of the references included in that paper. Whereas the Bose-Einstein paper is always co-cited with earlier work on the same topic. So we take this idea as to this kind of observation to represent the following fact. So the BTW paper launched a new stream of research, whereas the Bose-Einstein paper builds upon previous work, like standing on the shoulders of giants, like most scientific papers that we see in the literature. So we borrow the disruption index from Wu and Kotos. This is a Nature paper published in 2019. The mathematics of the index is very simple. The index is denoted by the tilde, and it's just you can see it in the slides. So we start from the Web of Science database, that is a database of published papers. Then we count the number, we take a focal paper. So the focal paper is the paper we want to measure the disruptiveness. And A indicates the number of papers citing the focal paper, but not the papers cited by it. Then we have another quantity, and B that is the number of papers citing both the focal paper and at least one of the references included in the focal paper. Then we take the differences of the two quantities and we divide it by the total number of papers. So the sum of these two quantities plus the number of papers citing at least one of the references of the focal paper, but not the focal paper itself. So you can see that by construction, this index ranges from -1 to 1. A value of d tilde close to 1 indicates a paper that conveyed disruptive ideas, that we have in mind radical innovation when we think about values of the index close to 1, while papers scoring close to -1 are more likely to be papers that develop, that build upon existing ideas, similarly to the examples that I provided earlier. And this is another way of calling it incremental innovation. So you extend an existing body of knowledge. In this paper, we are concerned with publications that have a value of the index close to 1. We are interested in measuring disruptive ideas. Just for instance, you know, in the paper, we go through a series of checks to validate this index. And for instance, Nobel Prize winning papers tend to score in the top percentile of d tilde distribution. So that is kind of reassuring that this kind of measurement, at least in part, is able to capture the novelty of ideas. Whereas like the review papers tend to score very close to -1. These are papers that takes a lot of citations because they cite many different articles, but they do not really convey a radically new idea. Now, since the index is quite novel, I'd like to show you how it correlates with the more familiar indicators of research productivity, that is citation counts. So you can see that there is a U-shaped relationships between the two. To connect to the example I gave before, you can see that there can be papers with a very high number of citations that are not really disruptive. This would be dots in this picture that are in the left part, in the negative part of the horizontal line, close to 1. They might still get many citations, but not be disruptive, because these are papers that do not really propose something radically new that eclipses the attention of the papers it cites itself. So this is just to give you an idea of what we are measuring. And in particular, what we do from the Web of Science, we measure the disruptive index on considered publication P by team I in year T. So we have this measure attached to any paper, to all papers. Then we take the total number of publications by team I in year T, that we denote by NIT, and then we just we take the average. We take the average disruptiveness of a team I in year T, because as you will see, we will be working with an identification based on team year variation. And also to ease the interpretation of our results, and to be sure that we're really capturing disruptiveness, we will be working mainly with a dummy variable that takes value 1 if the average team disruptiveness is above the 90th percentile of the d tilde distribution in the sample. Now, how do we define teams? In our setup, a team is defined as a group of more than one author publishing at least one paper together. Okay, and so we construct these teams based on the affiliations that are printed on the published paper that we take from the World of Science database. And how do we infer whether a team is collocated or distributed? So first, let me give you the definition. Collocated team is a team in which all authors are affiliated to the same research institution. And you will see that we will consider these teams the most likely to undertake face-to-face interaction when they work on the project. At the same time, a distributed team is a team in which at least one co-author is affiliated to a different institution. Just to clarify, sorry, to clarify, for instance, Cinci, Carl, and myself this year have the same affiliation. So if we publish a paper this year, we would infer that we work together. We work in a face-to-face interaction manner, okay, because we are in the same institution. If instead I was at MIT, so I had another affiliation, the same paper would convey the information that we are a distributed team, because at least one of us is in a different institution. So the idea is pretty straightforward. Now, once we have done that, we need to do a bit of cleaning, actually a lot of cleaning. Why? Because we need to restrict our focus to teams in which authors, in which team members have only one single affiliation. And why we have to do that? Because suppose that in my team I had two affiliations, so Oxford Martin School and MIT, then from the researcher, from the analyst, they cannot infer whether the actual research activities that we conducted were co-located or distributed, because we cannot find out whether I was in Oxford or in Boston at the time of writing the article. So we drop teams in which members have multiple affiliation, and this results in a 40% decrease in the total number of teams that we have in our database. Then we need to drop additional 15% of teams in which authors report different affiliation in different papers in the same year. Now, these are not mistakes or these are not really coding mistakes. Is that, you know, authors can behave strategically and choose to put on one paper a set of affiliation, and one paper another set of affiliation, because there is no unique policy that journals require about affiliation. For instance, someone might prefer to include the institution from which most of the resources leading to the publication were taken, or some other authors would prefer to give just the current affiliation independently of where the research activity was conducted. So then we drop other 6% of papers because they publish in different research fields in the same year. It will become clear in a moment why we do that, because our identification strategy will exploit the research field in which the team publishes. So we need to do that. Finally, we drop other 26% of teams publishing in arts and humanities, and only focus on science-related fields. Why we do that? Well, because science fields tend to have much shorter publication cycles. Now, as we know, in economics, it might take 10 years to publish a paper, and that would be it would be endangering our identification strategy. I will be more precise, I think, in a couple of slides. So this is the data cleaning we do. Now, our biggest concern here is that by removing all these teams, and in particular, we are worried that by considering only teams with single affiliation authors, our data would not be representative. So what do? We compare key team level statistics in the full sample, and the full sample is where teams are allowed to have more than one affiliation, and in the single affiliation only data set, that is the one that we will be using in the analysis. Now, reassuringly, as you can see, the statistics in terms of the share of disruptive work, the number of citations, the number of papers, and the size of the teams are pretty similar across the two databases, and this is kind of reassuring to us. Now, after going through the cleaning procedure, we end up with an unbalanced panel of over 56,000 research teams publishing papers over 49 years, from 71 to 2020. Now, we notice that 90% of the teams we observed are in the data for less than 5 years. And 90% of these teams change their spatial distribution. This is important because it's the variation that we are going to exploit for the identification. So that means that of these 90% of teams that changes between co-located and distributed, 80% of this move from being co-located to distributed. So basically, Cinci, Carla, and myself start off together in Oxford Martin, and in some year I go to MIT, and then we split. So from a co-located team, we infer that we became a distributed team. And only 5% of teams change status multiple times. So here are the summary statistics. I will just skip them for the moment, and we go on the empirical strategy. Now, the basic model is very simple. We want to relate disruptiveness with the dummy variable I described earlier to a dummy variable equal to 0 if all members of team I are affiliated to the same institution in year T, and equal to 1 if at least 2 members have different affiliations. So, as the name of this dummy suggests, we take these indicators to flag whether a team is distributed or not, or co-located. Now, sorry, despite the simplicity, we have several problems we have to tackle econometrically. So the first one is measurement errors. Now, I think that using this kind of notation, it's easier to describe the issue. So I hope I'm right. So let script APIT be the set of affiliations printed on publication P by team I in year T. Our one crucial assumption we make is that script A reveals the actual location of research activities that lead to publication P of each team member. Now, it is clear that this assumption is violated, for instance, if script A includes current institutions, but the project has been completed in T-1 when at least one member was at a different institution. Here, an example can be useful. Suppose that Cinci, Carl, and I managed to publish a paper this year. And suppose that our policy is to put current affiliation, although we have been working on the project for several years. And while we were working on the project, I was affiliated to the World Bank. Okay, so actually the project has been, the research activities leading to the publication was carried remotely through a remote collaboration, because I was in the World Bank office. But actually, we managed to publish the paper once I've joined Oxford Martin. So clearly, this violates our assumption. But also, the example let us notice that assumption 1 is much more likely to hold if the time from the generation of the idea and the publication is very short. So this gives us a first reason why to focus on science projects. Now, we don't have hard data on publication cycles, especially from idea to publication in different disciplines. But in science, it is much more frequent to write up, like, for instance, the results of a simulation, or in material sciences, a test of materials. It's much more likely to be shorter than in social science, like, or in history and arts, for that matter. Now we have other two problems. Basically, we have all the econometric problems we can think of. We have also reverse causality and omitted variable bias. In particular, assumption 2 is that our dummy for a distributed or collocated team is as good as randomly assigned. Now, clearly, this is violated if there is reverse causality. Suppose that disruption affects the spatial distribution of the team. So, for instance, suppose that a collocated team writes a brilliant paper. Now, this brilliant paper circulates through a working paper version of it that gets a lot of attention, a lot of traction, potentially many citations. And so what happens is that one member of these initially collocated teams get a job offer from Harvard, for instance. Now, suppose that this researcher accepts the offer and goes to Harvard. Then in this case, the dummy for distribution is equal to 1, but it has been affected by D. Okay, so a typical example of reverse causality. Also in this case, assumption 2 is much more too likely to hold if the time from idea to publication is short. Why? Because there is less time for the working paper version of the paper to go around and affects the job prospects of the authors. But then we have also another issue. That is a classic case of omitted variable bias. So suppose that there are unobserved team characteristic affecting both D and dist. So for instance, imagine that the team is composed by superstar authors, very smart people, so that the average team level ability is high. But this obviously can affect both the probability of producing disruptive work, but at the same time can also affect the job prospects, the job offers, the portfolio job offers that each team member has. So in that case, the dummy for distribution is not as good as randomly assigned. So what do we do? Here, the length of publication cycles cannot help us. So we just need to modify the error structure of our regression model and keep it as simple as possible. What do we do is that we include team level fixed effect as well as research field year fixed effects. Now, our regression model, what we'll be using is model 1, as you can see, is a linear model. It's a pretty parsimonious one. So UI absorbs time invariant team specific characteristics such as ability, as mentioned in the previous example, and the research field year fixed effect absorbs potential confounding characteristics, confounding factors, time varying, that can affect the probability of producing disruptive research, and also the tendency to work on site or in a distributed manner. For instance, suppose, this is just an example, suppose that in mathematics there is a higher chance to produce disruptive work, but also less tendency to work on site, because in abstract mathematics you don't need the equipment, you don't need things that are attached to a particular geographical location. Okay, so we hope with this fixed effects to purge out the estimates from these effects. And after including the full set of fixed effects, we just assume that the dummy for distribution and the error term epsilon are uncorrelated, so that we can consider distribution to be as good as randomly assigned across teams. But then what drives the dummy? What drives the identification? Well, we think that variation in the distribution dummy might be driven, for instance, by personal circumstances. For instance, suppose that the partner of one of the collocated team member get a job offer in a different city, that will lead the team to split for reasons that are largely unrelated to the disruptiveness of the research, or that one of the authors meets randomly someone at a conference or at the supermarket and gets a job offer that leads the author to go somewhere else. Now, okay, 25 minutes. I'm going through the results. Please, of course, if you have some question, feel free to interrupt me or to write in chat while I'm speaking. So here is our main result. So there is a negative impact of spatial distribution on disruptiveness. You can see that our our estimated parameter is negative and significant at 1% level. The magnitude it's pretty small, I would say, on impact, because to interpret this coefficient, for instance, it means that a team switching from being a collocated team and a distributed team is roughly 1 percentage point less likely to produce disruptive research in a given year. Okay, so essentially we can interpret equation 1 that I showed before as a linear probability model in this setup. Okay, so 1 percentage point less likely to produce disruptive research due to spatial distribution. And essentially this is our main result. Now we try to analyze it further. One of the most important questions is this effect transitory or it is persistent? So to find out that, we estimate an event study regression, okay? And we include 4 lags and 4 leads. We limit ourselves to 4 plus and minus because, as I told you, in the earlier on, we observed teams, most of teams for no longer than 5 years. Okay, so if we add more structure here, we get everything not significant for that reason. But so, what is the most important point? This figure shows the estimated coefficients from the event study regression and the 90% confidence interval. You can see that there is a negative and pretty persistent impact up to year 4. This is in year 2 there is some noise, but I think the picture is pretty clear. The impact is negative, long-lasting, and even increasing. In year 4, the maximum, the largest value in absolute terms is over 0.05. That suggests that in year 4, a distributed team, a team that was collocated in -1 but became distributed at time 0, 4 years after is 5 percentage points less likely to produce disruptive research. So the negative impact of spatial distribution appears to be persistent over time. Now we experiment with more familiar indicators of research productivity. In particular, in column 1, we show that switching from collocated to distributed is estimated to have a roughly 12% lower number of citations per year. Also, the number of published papers per team is lower, like 2.5%, and the number of citations per papers, almost 10%. Lower for distributed teams. Also, now in column 1 in this table, we use the raw value of the index, of the disruptiveness index. And you can see that the results are qualitatively identical. You have a very significant negative impact of spatial distribution on disruptiveness, although it's much smaller in magnitude, but this is because the index tends to be distributed around 0, okay? So a change by 0.001 is still a significant decrease in the value of the index due to geographic distribution. Now in column 2, we just use a dummy variable as in the baseline, but we use the 99th percentile of the distribution as a cutoff rule, and still we find very similar results. Now, as I told you, this is we are working with a linear probability model. There are many zeros, almost 80% of zeros for the dependent variable. In other words, only 20% of the papers, or sorry, of the teams are producing disruptive research. In our data, there are many zeros, so we experiment with a fixed effect logic model. The picture, but unfortunately, we are using state as a statistical software. We experience problems of convergence of the likelihood function here. And so we need to change the baseline specification. In particular, we managed to solve the problem by removing research field year fixed effect, including instead field year trends and year dummies separately. So in that case, we managed to get an output. The coefficient is negative and strongly significant, and much larger, not surprisingly in magnitude, 13%. 13 percentage point less likely to produce disruptive research according to this estimator. So essentially, we think that while we consider our baseline specification, the linear probability model, still our preferred one, since we can include the field year fixed effect, we notice that that negative impact of 1 percentage point should be considered as an upper bound effect. The actual effect could be even larger. This is the information conveyed by column 3 in our opinion. And finally, as a robustness test, in column 4, we run the baseline specification, but we do not drop science. We just we keep all the research fields. So for instance, economics is inside it now, and results are remarkably similar also in this specification, although the number of observations is much higher. Apologies. So all in all, spatial distribution appears to be detrimental to research productivity, and in particular to research disruptiveness. So what is the underlying mechanism? Our working hypothesis is that the lack of face-to-face interaction across team members hinders creativity, serendipitous discovery, and the communication of tacit knowledge, and probably other kind of friction, communication, coordination friction that might arise by not being in the same room with your team members working on a project. But that being the case, if that is really the underlying mechanism, the underlying reason for the negative correlation between spatial distribution and disruptiveness, then it might be the case that a better information and communication technology infrastructure and the better communication technologies more broadly should mitigate such negative impact. Now, as you know, over the last decades, there are a host of communication technology, coordination and communication technology have been released, for instance, Skype in 2003 and Dropbox in 2007. But, many of these at least became more widely used in recent years. Like, for instance, Trello and Office 356 in 2011, Zoom, Google Drive 2012, Slack, Overleaf, Teams, and so on. And these are relatively recent technological achievements. So better ICT infrastructure, our finding in this table is that better ICT infrastructure does mitigate the negative impact of lacking face-to-face interaction. At least this is what the evidence tends to suggest. So what do we do here? We take for every team the country hosting the institution, the country of the institution hosting each team member. And for each team, we compute the average number of internet broadband subscription per capita. So, for instance, if I'm in the US, Carl and Chinchi are in the UK, we take the number for every year, the number of internet subscription in the UK and in the US, we compute the average per team, okay? And then we interact this quantity with our main dummy variable. You can see that in the first line, the distributed team coefficient is still negative and statistically significant, although the impact is muted when the team is involved. The team operates in countries with a higher number of internet broadband subscription per capita. Now, of course, in the third line, for the construction of, for the econometric setup of this regression indicates the impact on disruptiveness of broadband per capita for co-located teams, and not surprisingly, still positive and significant, because even if you are co-located, you use the internet to look for information, to communicate with other people. I'm just getting a message. Yes, I will get into a moment into that. Actually, it's the last part of the storyline. Thanks for the question. Here we are. So consider this picture. It correlates the share of distributed teams on the horizontal axis and the share of teams producing disruptive research on the vertical axis. As you can see, there is a negative correlation up to around 2010, and then the negative correlation becomes flatter for the latest years, you see? So this this evidence, this descriptive evidence, fits very nicely the emergence, the release dates of the modern communication technologies that I mentioned before. So, in principle, this supports our working assumption. Now we go to investigate this relationship a bit more formally. So here we essentially estimate the relationship between disruption and spatial distribution by time period, in particular before the 90s, when the ICT revolution started, between the 90 and the 2010, after 2010, and then after 2015. So this is related to the question I just asked, been asked. You can see that the impact is negative for early years of the sample, so from the 70s to the 90s. Then it's still negative, but it tends to become closer to zero up to 2010. And also in the last years of the sample, last 5 years of our sample from 2015 and 2020, we find a positive and significant coefficient. So actually the impact of spatial distribution seems to be reverted in the latest years. So even if communication technology can mitigate the negative impact of lacking face-to-face communication, then we ask, why should spatial distribution have a positive impact? Well, there are benefits of remote collaboration. In fact, as I showed you in the first figure, the share of remote collaboration has been increasing over the years. So it is natural to think that there are benefits from remote collaborations. So we theorize that there are two countervailing effects. The first one is the one we mentioned up to now, is the lack of face-to-face interactions that contributes to negatively affect disruptiveness. The second impact is actually positive, and it includes the complementary knowledge, skills, and assets that a distributed team can benefit from. So for instance, if I'm at MIT, I might, I don't know, use MIT machines or attend their seminars, get feedbacks on the ideas that I'm developing with Carl and Cinci in Oxford. But what happens is that when we could not communicate efficiently, this knowledge failed to spill over to my previous collaboration, to my remote collaboration. But when Zoom kicks in, I'm able to really communicate, to replicate as closely as possible face-to-face interaction, and this is precisely in that moment that the complementary effect, the benefits of remote collaboration, can really have an impact of disruptiveness. So we try to test these effects by calculating for each team the average university ranking. So we just take the Financial Times latest ranking. We attach to every institution we have in our data set that score, and then we sum it up, we aggregate it at the team level. And then we build a dummy variable that takes value 1 if the average ranking of a team improves in a given year. So we lose observation because not all the institutions we have in our data are in the FT ranking. So we lose a few observations. But the message is pretty clear here. When we interact the dummy for better university ranking with the distributed team dummy variable before 2010, we do not find any significant effect. Actually, the coefficient is even negative, although the standard errors are much, much larger than the coefficient, so we cannot really say anything about that. But when we interacted this double interaction, we interacted with a dummy variable taking value 1 since 2010, we do find that the impact is reversed. So essentially after 2010, with better communication technologies, while there can be a knowledge spillover from the resources that I find at MIT, and I can spill them over to my remote collaboration in Oxford. This is essentially the way we interpret this evidence. let me just give some tentative conclusions about what we discussed, and then I'm looking forward to discuss and answering questions. So we find that over the last decades, there was a rise in remote collaborations, and our evidence suggests that the lack of face-to-face interaction might be the underlying cause of the decline in radical innovation. So our findings, actually, I skipped the literature review for obvious reasons, but our findings speak to the intuition of a recent paper by Bloom and co-authors, and EAR papers titled "Are Ideas Hard to Find?" And they, with a completely different approach, they show that the research productivity in science has been decreasing over the years. So, you know, the lack of face-to-face interaction due to remote collaboration can be one of the factors contributing to this general decline in the novelty and disruptiveness of ideas. We find the last generation technology do mitigate such impact, you know, our results speak to the intuition that ICT have clearly many benefits for productivity from many economic variables, but one key role is that they might help enabling this kind of interinstitutional complementaries through knowledge spillovers. And that's all I wanted to say. So I will stop sharing the screen and